Welcome to the sixth lecture of the course turbulence. So, as usual let us start with a brief recap of the previous class. So, in the last class we have talked about the disturbance growth and its nonlinear interaction, and we found at the end of the class that due to the nonlinear interaction of the disturbances there can be different modes be excited or different modes can be excited due to the nonlinear interaction of the disturbances. Okay. So, essentially stability analysis gives us a kind of guideline from which parameter value honored of a parameter, for example, it is Reynolds number or Rayleigh number or any other parameter beyond which a disturbance is going to grow. So, this is what comes out from a stability theory or analysis. Then once the disturbance is growing in space or in time, what it may happen, its amplitude will be sufficiently high enough to trigger nonlinearity in the flow. As a result, various scales will be generated in the flow, and due to that the laminar flow will be slowly taken to some other state which may be chaotic enough to be or may be turbulent. Okay. So, for example, if we take one very small example, for example, the flow over a flat plate. Okay. So, if you consider flow over a flat plate at a very small level of disturbance. Okay. So, let us say this is your a flat plate and there is a flow over this flat plate, and there is a very this flow is under sort of there is an uniform flow, and in that uniform flow a plate is submerged which is flat enough or thin enough. Okay. The disturbance level in the free stream is very small. So, in that case what will happen, if the Reynolds number is let us say beyond 520 based on the displacement thickness, then what will happen, there will be some two dimensional perturbation which will grow like that. Okay. So, two dimensional perturbation, if you put a hot air probe somewhere here, let us say this is your hot air position, okay, hot air probe, and if you registered the data from this probe, that probe due to this passage of this wave, the probe signal will be something like this. Okay. It is a wavy nature. Okay. Somewhere downstream this particular wave start three dimensional or three dimensionality will be developed, and due to this three dimensionality somewhere downstream what will happen, the flow will be will be broken down to turbulent flow. Okay. So, there will be a small spot of turbulence will be generated. Okay. So, this is what is your small spot of turbulence. Similarly, there can be another spot somewhere here. Okay. So, these are kind of small packets of turbulent within a laminar flow. Okay. So, these are the small packets of turbulent, and these packets of turbulent eventually merge together as they go downstream. Okay. So, let me increase the length of the plate, let us say somewhere here. So, as this spot will go downstream, they will merge together, and make the flow totally turbulent. Okay. So, this is what is your completely turbulent flow. Okay. Okay. This is what is your completely turbulent flow. So, somewhere here if you keep your hot air, let us say somewhere here you are keeping your another hot air and registering the signal of the flow, and somewhere here another hot air, let us say. Okay. And if you take this let us say this is position 1, position 2 and position 3, if you take these three position data in the process of transition over the flat plate, let us say this is your fluctuating quantity and this is your time t, then this is at position 1 the velocity signal will something like that it will look, and at position at position 2 your fluctuating velocity signal will sometime look like this. Okay. So, this is your once again time. So, these are the packet of spot turbulent patches. So, this is once again in time. So, I have already written it. So, these are the patches of turbulent flow, and these signals are registered when these kind of patches are passing by this hot wire, and this kind of high fluctuation signal will be noticed in the hot wire trace. Whereas, if you take the signal at this location 3, you will be able to see that your fluctuating signal will be completely fluctuation for all these time periods, okay, or for all for entire length of the time. Okay. So, this is something like your turbulent signal at position 3. Okay. So, this is once again your time and this is your velocity fluctuation. So, this this signal is actually due to this passage of this Tolman and Schlichting wave. These are called as TS wave or Tolman Schlichting. TS means Schlichting waves. Okay. These are 2-dimensional wave, then this becomes 3-dimensional wave, and these are turbulent spot. Okay. These are turbulent spot, and then finally, the fully turbulent flow. Okay. So, these are the stages of transition over a flat plate. Okay. We have also talked about how we can figure it out the position where the flow is completely turbulent. So, based on that, I mean based on some correlation technique or some semi empirical linear stability based technique we have talked about in the last class, based on which we can predict the transition location. Okay. So, anyway, this is what I just wanted to ensure, that once there will be one wave will be excited, this wave as its amplitude increases, then it will trigger nonlinearity in the flow. Due to that or due to nonlinearity, this particular wave can generate all other waves in the flow, and eventually the flow will be taken to a turbulent state, and that before fully turbulent state there will be some packet of turbulent like that for this particular type of flow. So, this is for your flat plate case. Okay. Flat plate boundary layer. Okay. So, for the case of flat plate boundary layer, this is what is the scenario. Okay. So, now today actually, since we will be only talking about this particular state in this course, so how we can describe this kind of signals. Okay. So, this is what will be the topic of today's discussion. Okay. So, anyway, so let me start that. So, basically we are going to talk about some averages and standard deviation, variance, then correlations. So, some of the techniques we are going to talk about today. Okay. So, let us consider two geometry once again. So, to start with so we are going to talk about averages, various averages. Okay. So, before we proceed, let us consider two type of flows. For example, one turbulent pipe flow or turbulent channel flow, whatever you consider. So, let us say this turbulent channel flow, different kind of eddies will be present. Okay. So, different size of eddies, small, large, medium, different kind of eddies will be present, and it will be full of eddies in a turbulent pipe flow. So, let us say this is your turbulent pipe flow. Okay. And another case let us consider, that is, let us say there is a tank and let us say this tank height is sufficient enough and it is full of some liquid, let us say water it is, and let us say there is a nozzle here through which the flow is coming out. Okay. the flow is coming out. Okay. So, the pressure at this particular point is h rho z, right. So, this is what is your free surface of the liquid. Okay. So, now let us say we will keep a probe, let us say we will take a probe, we will position a probe somewhere here in this particular case, and so it is a probe location. Okay. Probe location, and let us take another probe location somewhere here, that flow is coming out. So, another probe location is here, let us say. Okay. So, this is also a probe location. Okay. And let us say the flow through this pipe is occurring at some particular velocity, and the velocity is constant. That average velocity through average velocity in the center line of the pipe is constant. Okay. Now, if we consider the time series signal for this particular case, let us say that velocity signal rather we will talk about at this point of time. So, let us say this is velocity signal, and the velocity signal, if you see, it is random, something like that, sorry, it is something wrong. So, it is very random. So, it will show something of this sort. Okay. So, this is your velocity signal at this location. Okay. At this location, see, this is the velocity signal. Okay. Similarly, for this case, if we draw the velocity signal, for this case if we draw the velocity signal, so what is happening? You see, as you open the exit, then water will come out from this tank, and the height of the water will slowly come down. As a result, pressure at that location will reduce slowly with respect to time. As a result, your velocity of this jet will also reduce. So, and this jet is considered to be highly turbulent. That means, your velocity will reduce like this. Okay. So, this is your velocity signal for this particular case. Okay. So, velocity is continuously reducing at the head of the water in this particular tank is reducing. Okay. So, there are two type of fluctuation, as you can see here, that it is sort of constant about this particular line. Okay. Sometime it is positive, sometime it is negative. What about this? This, if you draw a line something like that, about this it is sort of positive and negative. So, when we are talking about averages, we have to be careful about the flows and their type of variables we are considering. Okay. So, generally the variables in turbulent flows. So, basically turbulent flows are not deterministic. In details, and therefore, we have to consider these variables to be stochastic or random variables. Okay. So, the variables in turbulent flows needs to be considered as random variables. Let us say velocity for this particular case, if you see velocity for this particular case, as you are increasing time, this particular velocity is just fluctuating about this particular line. So, if you take average with respect to time for this particular type of signal, the average is not going to be a function of time. Okay. Whereas, here if you see for this particular case, if you take the average based on the length of a particular time, if this is the length, then your average value will be something like that. If you increase the length, then your average value will be something like that. If this is the length of time over which you are averaging, your average is continuously changing with respect to time. Okay. So, these two cases you see are different. Okay. So, this particular type of signals is known as stationary. And this is not stationary. Okay. Signal, a stationary signal. Okay. So, for this kind of cases, if we define the average as, let us say for this the first example, if you consider the averages, so the average can be defined as that variable u bar means it indicates the average. By definition, we consider this to be 1 by capital T, then T naught plus capital T u of t dt. Okay. Okay. So, this is what actually average is defined over a period of time, okay, on which beyond which if you consider the t, the average will not change. What I would like to mean, suppose this is your length of t, you should consider that length of t. Suppose if you consider this length of t and found out the average and got the value, increase your length of t of averaging, and this is what is your t now. If you find this average also does not change, that average over this length and average over this length is same, then this t is sufficient enough to take this particular length. Okay. So, the length of t should be sufficient enough, so that average is independent of time. Okay. And here the t naught, I can start the averaging process, okay, at a location t is equal to t naught, okay, and take the average over a large time t beyond which the average will not change. Okay. So, this is what is our sort of time average. So, this time average is not a function of time, and if this time average is independent of t naught, then that process is known as stationary process. Okay. When this average does not depend on the origin of t, the t naught, or for a stationary process it is independent of this t naught. Okay. That is what the point. Whereas, in this particular case, we cannot take average in this fashion. Whatever may be your t, your average will keep changing with respect to the time length. So, what is the way out? Okay. So, we need to find a way out for this kind of signal. So, for this kind of signal, something called ensemble average. So, we have to find out the ensemble average for this kind of signals. Okay. So, this particular type of average, it is known as sort of time average. Okay. So, this is time average, and for these kind of signals we have to carry out the ensemble average. Now, For ensemble average, what we have to do? Okay, we have to take several repetition of that experiment. For example, that experiment whatever we have done there. So, if we do that experiment at a particular day and got this signal as this. So, this is your u of t versus t. This is one realization or sorry one experimental data. Okay. Then you repeat this experiment, again you fill the tank, once that liquid is over in the tank, then again take another experimental data at the same location under identical condition, the condition we cannot change. Okay. Under identical condition we have to take another data and you will get another series like this. Similarly, keep repeating this experiment. Okay. So, you have many such data which you generated using repeating the experiment at different time, but under identical conditions, and in that case you got many series like that. Okay. Let us say this is your u 1 of t, u 1 of t, this is your u 2 of t, this is your u 3 of t, means first time experiment this is the signal, second time experiment this is the signal, third time experiment this is the signal of u. So, how to define this average then? What we can do, instead of averaging in time for this kind of signal, what we can do, average in this direction, add this plus this plus this, maybe then another n number of experiment like that, then divide by n and then you will get a line. Okay. And that particular average will be a function of time as well. Okay. So, that is what is our ensemble average, means you are actually generating many ensembles by doing many experiments. So, by doing many experiments you are just getting many ensembles and adding them together to find an ensemble average. Okay. So, that ensemble average is defined as, so ensemble average by definition 1 by n, okay, I is equal to 1 to n your u I of t. Okay. So, this is what is your ensemble average, which is actually, you see this is nothing but your u 1 of t plus u 2 of t plus dot dot plus u n of t. So, you have n ensemble, you are just adding them and dividing by the number of ensemble and then you get the average, and that average it will come as this. So, this line is your ensemble average, this line is your ensemble average. So, this line is, you see, still is a function of time. So, that average itself is a function of time, although it is constant, although it is straight actually, it is not fluctuating, but it is a function of time. Okay. So, this is what is your ensemble average. Okay. So, one thing to keep it in mind, when your signal is stationary, means when your time average does not change with time, if you average over a sufficient period of or sufficient length of time, then that is what is your stationary signal. So, for a stationary signal, ensemble average and time average are same. Okay. For stationary process, the time average and the ensemble average are same or identical. Okay. So, this particular average is known as, so this equation what I would like to mean. So, this is known as ensemble average. Okay. So, we should be very careful which average at what time we need to do. Okay. So, this is one thing. Another, there are some properties of this average quantities. Let me just quickly discuss. For example, that ensemble average is this. Okay. Suppose we would like to average the derivative of this signal. Okay. So, this signal, keep it in mind, can be a function of space as well, because we are writing it is a function of time, because we have taken that signal at a particular location in space. Okay. That is why we are just writing it is a function of time. Keep it in mind that this signal is coming basically from this particular point. Okay. So, if you take some other location, if you put your hot air probes at some other location, the signal will be a little bit different. So, it is a function of space as well, but since we are talking about the average at that particular location, so it is a function of time only. Okay. So, anyway, now let us see. So, we have understood there are two type of time averages for the fluctuating variables in a turbulent flow, and one is ensemble average, another is your time average. All right. There are some property. Okay. So, for example, that we would like to get an average of this quantity. Okay. Yes, let us say we would like to have the average of this quantity. Okay. So, how to get this average of this particular quantity? So, what we can do in that case, see, we can go by the definition. According to definition, ensemble average definition of this, let us consider for simplicity. So, if we consider that, so then by definition it is actually del u t 1 plus this is 1 del u 2 t dot dot plus n t, okay, and this can be this can be written as 1 by n u 1 of t plus 2 of t plus n of t. Okay. So, this is equal to what? This is already we have defined, and that is nothing but your u bar. Okay. So, that means that one property of this average, you see that this average of this derivative is equal to the derivative of the average of the variable. Okay. So, this is one property. Similarly, you can show integral a to b u of t dt, okay, average of these equals to integral a to b u of t dt. So, these are some of the properties. Similarly, you can get many such properties. For example, two variable, let us say f and g are two turbulent variables. Okay. If this is the case, then f plus g, average of these can be written as average of this plus average of this. Why? What is the average of this? Average of these, let us say the time average we would like to consider. So, average of these integral. So, if we consider time average of this, we can write 1 by capital T, T naught plus capital T, that f plus g dt. Okay. So, this is equal to, you see we are starting from the left hand side, okay. LHS is equal to this, is equal to, this can be written as T naught plus capital T dt plus T naught plus capital T z dt, f and g let us say function of time. So, in that case this is equal to what? This is the what? This is the definition of f bar plus this is the definition of z bar, right. So, there are many such properties. For example, I want you to check z bar what will be the average of this quantity. So, this is equal to, show that, okay. So, you do this exercise, show this is equal to f bar and z bar, okay. Similarly, so this is 1, okay, 1. Similarly, show f bar is equal to f of bar, okay. So, this kind of there will be many things. So, some more we will add. So, let us do one thing, there are more definitions, let us finish some of the definitions. So, something called variance. What is called variance? So, the mean square value of a variable or random variable is known as variance. Okay. So, what it says, let us say this is what is your variable. So, mean square, mean then square, okay. This is the symbol which is designated for mean. So, mean square value is the variance. That means that by definition variance by definition is this, okay. So, what is known as RMS, root mean square value. So, the square root of the variance, the square root of variance is known as root mean square or simply RMS of a variable, okay. So, what it says RMS RMS of a variable, let us say u. So, u RMS is square root of variance, or this is equal to simply your variance square mean, okay. So, this is what is defined as RMS, okay. Now, let us say mean is removed from this u of t variable. If you remove the mean, means if you write your fluctuating quantity as u of t minus u of t mean. Okay. So, if you subtract the mean value from this instantaneous value, so what is your instantaneous value? So, remember our pipe flow experiment. What we did? We have plotted u of t versus time at a particular position in the pipe, and we found for a stationary pipe flow it is highly fluctuating in nature. So, if you do the mean, this is what is your mean, okay, which is independent of time. Okay. Mean is not a function of time, its frequency is 0, okay, because there is no oscillation. So, the time period is infinity. So, frequency is equal to 1 by t, right. So, 1 by t, the capital T frequency, what is f? F is equal to 1 by t, right, and this t the time period, and the time period is infinite here. So, that means f is equal to 0. Okay. So, your average is this straight line. So, if you remove remove mean from this instantaneous signal, okay, for example, at this particular location, what is the value of this? Let us say at this particular location, the value of u prime, which is the fluctuating quantity, is positive, right, because your u instantaneous value from here to here, u instantaneous from here to here, this is your u instantaneous minus your mean, mean is what? Here to here. So, this is what is mean and this is what is your instantaneous. So, the fluctuating quantity is this much. So, this is the value of the fluctuation u prime. So, that is positive in this case. What about this case? Somewhere here, for example, somewhere here. So, your instantaneous value is this much. This is what is your instantaneous value, this is what is your mean. So, this minus this minus this. So, your u fluctuation, it is less than 0 here, whereas it is greater than 0 here. So, if we plot only the fluctuation, you see, if we plot only the fluctuation, means after removing the mean from it, if we remove the mean and plot the fluctuation, it is going to come like this, okay, because this is what is your time, this is the 0. So, with respect to time, sometime it is positive, sometime negative, sometime positive, sometime negative. Okay. That is what is going to come if you subtract the mean and plot the fluctuation. I cannot exactly replicate the same series here, but I believe that you understand what I wanted to mean. So, this particular quantity u prime, if we subtract the mean from here, we are going to get sometime positive, sometime negative, sometime positive, sometime negative. So, if we would like to tell, suppose we would like to say what is the level of turbulence, how to measure the level of turbulence. It may so happen for some turbulent flow, if I plot the fluctuating quantity u prime only, it may so happen for that it is this much fluctuation. Okay. And for some other turbulent flow, it may so happen that value is very small in the same scale if we plot. Okay. So, qualitatively, if you plot keeping this scale as same, let us say this scale is minus 20 to minus 20, this also you have plotted from minus 20 to 20. In that same scale, if you see them, one is very high fluctuation, another is less fluctuation. So, how to say this particular flow is highly turbulent, this particular flow is, I mean qualitatively the moment you plot you can say it, okay. But without plotting, just by knowing this fluctuation u prime at a particular point in time, we cannot say it is highly turbulent or not, because it is fluctuating in nature. At later point of time, its fluctuation can be very high or very less. Okay. So, just by judging the fluctuation at a particular point in time, we cannot say the flow is highly turbulent or I mean mildly turbulent or turbulence level is very small, we cannot say that. So, what we need to do in that particular case? In that particular case, if we find the RMS value of this quantity, RMS value of this prime quantity, that RMS value of this prime quantity is going to be higher as compared to this signal. Okay. So, what is this RMS quantity? You are just removing the negative. So, all negative, because u prime square, then you are taking the mean. So, first you are taking all these signals, squaring the signal, whether it is positive or negative does not matter. You are just squaring, then taking mean, then taking square root, that is what is your RMS. So, that means RMS of this fluctuation, if this is very high, then RMS of this signal will be high and RMS of this signal will be low. That means, if we know the RMS value of that fluctuation for a particular turbulent flow, based on these RMS values, we can we can say whether that particular turbulent flow is highly turbulent or what is the turbulent level in that flow. Okay. So, based on this quantity we can say turbulence level is low or high. Okay. So, this RMS of this fluctuation is actually your variance, and when it is mean removed, it is also known as standard deviation. Okay. So, this if you square this, take the mean, take the root, that is also known as standard deviation when you are removing the mean, keep it in mind, or RMS of this fluctuation. So, please do understand, while describing a turbulent flow, whether it is highly turbulent or not, if you calculate the RMS value, that u RMS value, u prime RMS value for this particular case and for this particular case, if you compare, then RMS value for this particular signal will be much less as compared to RMS value of this signal. Okay. So, higher the RMS value of a fluctuating quantity, higher the level of turbulence. So, these are the, so RMS can serve as a measure of turbulent flows. Okay. So, RMS can serve as a measure of turbulent flows. Okay. So, usually suppose we would like to say, very often we say that less turbulent intensity or highly turbulent flow or high turbulent intensity, that all based on these some sort of RMS measures. Okay. So, usually in a free stream, the turbulent flows, in a free stream the turbulent flows are defined based on the turbulent intensity. So, what is the definition of turbulent intensity? I think it is important to consider here. Okay. So, the turbulent intensity we define as, so turbulent intensity by definition you can call it Ti. Okay. By definition you can consider u RMS prime square plus V prime RMS square, sorry, there should be a bar here, there should be a bar here, okay, plus W RMS prime square bar, okay, divided by 3, okay, divided by 3, 1 by free stream velocity u infinity, okay, into 100 to make it percentage. So, this is the definition of turbulent intensity percentage in a free stream flow. So, here the measure is considered not only based on your u prime fluctuation in a particular flow there can be 3 component of a velocity in a Cartesian coordinate system. One is u, another is v, another is w. For a 3 dimensional flow, 3 instantaneous velocity. So, for a 3 dimensional flow, we have considered u t, then similarly there will be a value v t, similarly w of t. Okay. So, these are the instantaneous value, okay. Instantaneous value, velocities, okay. These are instantaneous velocities. Similarly, you can define the fluctuating velocities. Fluctuating velocities are defined as we have already mentioned for this particular case. So, this is u of t minus u bar of t. Similarly, v prime of t is equal to v of t minus v bar of t, or v bar simply, because it is not a function of time if it is stationary signal. If it is non stationary, yes, it can be. And then we have w prime of t is equal to w of t minus w bar. Okay. So, these are the fluctuating velocities, and each and every component of this fluctuating velocity can have a RMS value. And to define the free stream turbulence intensity, what it has been done that actually I have made a mistake here, I should not keep this RMS. Okay. This is not called as RMS, sorry. Okay. So, it is essentially u prime square v prime square bar then w prime square bar. So, u prime square bar, this is nothing but u RMS square, v prime square bar, this is nothing but v RMS square, w prime square bar, this is nothing but w RMS square. So, that means RMS square, RMS square, RMS square, then divide by 3, divide by free stream velocity, that is what is your turbulent intensity if you multiply by 100, okay, or percentage of turbulent intensity in the flow. Okay. So, all right, that means it is very important to understand what is called RMS values. Okay. So, if we remove the mean from a turbulent variables and take the RMS value, then that is a kind of measure of turbulent fluctuation in a flow, because since the fluctuation can be positive negative. So, no meaning of using the fluctuation as a measure, rather it is RMS, it is a measure. Okay. Keep it in mind. All right. So, now I would like to come back to this particular case once again. Okay. So, if this is the case, you can show that suppose f and g bar is equal to, you show f bar g bar plus f and f prime g prime means fluctuating this. Okay. So, show this I mean do this exercise and show this particular identities. Okay. All right. Now, we have talked about average, variance, RMS, standard deviation. Okay. Now, another important technique or important statistical technique, something is known as correlation. Okay. So, let us understand what is called correlation. Okay. So, this is also very important. Okay. Okay. Before I proceed, just one more observation I would like to show, that is RMS we have talked about of a fluctuating velocity signal, let us say u prime, but what about the mean of this value? what is the mean of any fluctuating quantity in a turbulent flow? The mean of any fluctuating quantity in a turbulent flow is 0. How? You see this, by definition we can write this u fluctuation is what? U instantaneous minus u bar, right. This is what it is. And now what is this? This bar means 1 by capital T, T naught plus T naught plus capital T. What is inside? U of t u bar dt, right. And you see 1 by t, let us consider the signal is stationary, u of t dt minus we can write this as 1 by t integral t naught plus capital T u bar dt, right. If it is a stationary signal, u bar mean is independent of time, it does not depend on time. If it does not depend on time, then what is this quantity? By definition is nothing but your u bar, and since it is independent of time, this quantity is also u bar. So, the average of this fluctuating quantity is 0. Therefore, you need to keep it in mind, average of any fluctuating quantity. For example, if you do this exercise for V prime bar, you will see it is 0, for W prime bar it is 0. Similarly, the pressure fluctuation P bar will be 0, temperature fluctuation, fluctuation let us say T prime bar, this will be 0. Okay. Any variable in a turbulent flow, any fluctuating variable average in a turbulent flow is 0, that is coming from this particular analysis. All right. So, now let us talk about correlation, which is very very important in the case of turbulent flow. So, now we are going to talk about correlation. Okay. So, correlation, there are different type of correlation, autocorrelation, cross correlation. Okay. So, first we will talk about autocorrelation. Autocorrelation, when a particular variable correlate with itself. Okay. So, for example, we are considering the u prime of t, correlation of u prime of t with itself. So, that correlation let us define R of T1 and T2 as by definition it is actually u prime at some time T1, u prime at some other time T2, and average of this is known as correlation. What does it mean? It does not mean anything. So, what it says, see, suppose there is a time series of u fluctuation, let us say, this is what is our time series and this is 0. So, its average is 0 and this is what is your time series u prime of t. See, if this is what is your T1 this time and this is what if is your T2, then you see u prime T1 into u prime T2 both are positive and both will give you a high value. But instead of your T2 is this, if your T2 is going to be just at this location or somewhere somewhere here maybe, then your this particular value is negative and the value is also small. So, this multiplication will be very small. So, that means this particular value, the numerical value of this particular average depends I mean how far these two time is considered, okay, sorry, how far these two velocity is taken, not two velocity, how far this velocity, single velocity, that is your free stream velocity, streamwise velocity, streamwise fluctuating velocity. So, how far they are taken in time. Okay. So, if you see that if this time is taken, t 1 is taken here, let us say this is what is your t 1 and another t 2 is here itself, just little bit away from it. Then you see one t u prime value is here, okay, another prime value is here. So, both the value are positive, both the value are very high. Okay. Similarly, if they are closely taken 7, this is what your t 1, another t 2 is, this is what is your t 2. So, when they are very close, when this time gap is very close, it is highly likely that their multiplication will be, that their this multiplication value is high. Okay. So, see this particular this particular idea is known as correlation, and from that we can find or define many things in turbulent flow. Okay. We will try to understand time by time. See this particular value from this, as I have tried to make you understand, that when this gap between t 1 and t 2 is small, their multiplication value is going to be high. Why? Let us try to understand pictorially what is going to happen. Let us say we have just talked about this pipe flow. Let us consider the pipe flow itself. Pipe flow, the eddy can be something like that. Okay. Let us say this is one eddy, another eddy is something like that. Let us say its fluctuation, that arrows I am drawing just to show the fluctuating velocity vector in this particular plane. So, this particular plane, if it is x and y plane, then these velocity vectors are made of u fluctuation and v fluctuation, that is it is made of u prime and v prime. So, these are different size of globes which loosely can be called as eddy, as I have mentioned. So, these are the fluctuation. So, eddy means what? The type of fluctuation within this packet is similar. So, this, see why this eddy? Because this fluctuation, all fluctuation are sort of in this direction. In this eddy you see all fluctuation sort of in this direction. In this eddy it is all fluctuation sort of in this direction. Okay. So, another eddy, let us say it is somewhere here, its fluctuation in this direction, and another eddy somewhere is here, is also fluctuation is this direction, another eddy even bigger, let us say its fluctuation is this. Okay. Now, see if I take a special series means what? Let us say this is what is our x, this is what is our y. Okay. And if I sample data very close like this, if I sample data like this at each and every delta x, then I will be able to draw a spatial series of data. So, instead of this is a time series, similar series I can make from this data a spatial series. So, just this is instead of t 1 and t 2, in that case I can write it is a function of x 1 and x 2, same thing, either the series in space or series in time. And here how I am doing it? I have just taken a snapshot of the flow and just taking a line and just finding the data at each and every delta x. Okay. Now, you see this is an eddy, and within this eddy you see the fluctuating velocity vector are always in this direction. That means what? Within this distance, if you multiply this u prime into u prime separated by this, that value is going to be always high. Similarly within this, similarly within this. Okay. So, on an average, if you take an average like that, so then for example this T1 and T2 are closely spaced point, okay. And let us say you have a data at this point, another data, let us say this is one data at a point, another data, another data, another data. So, these are all separated by either delta t or delta x, okay. All separated by let us say either delta t or delta x based on the time series or space series, right. So, for a delta t, only for one delta t, to get this average what I can do? I can multiply these data with these data, keep one sample. Similarly, I can multiply these data with these data, another sample I have got. So, to get that signal, the T1 minus or T2 minus T1 of the order of delta t, I can use these data and get a average value of this. Okay. So, that if this time gap is small, then it is a maximum chance of getting same level of fluctuations, that is what I was showing. See, if your time gap is small from here to here, your all fluctuation is positive. Okay. So, that means it is a very high chance of getting this multiplication factor or this quantity to be very high value. If it is very high, if the time gap is very high, this is not going to be so. Okay. So, this correlation value is high means, actually your signal is highly correlated, means basically it is highly correlated in the sense, see that correlation from here to maximum AD, suppose this is your maximum size of AD. So, one signal is here, another signal is here, if you take suppose your T1 or x1 is here and x2 is here, then this signal and this signal is most likely to be uncorrelated. That means, this value is going to be almost negligible beyond the largest size of the AD present in the flow. Okay. Because you see, if this is the AD size, the maximum size of the AD, this value is going to be non-zero, because the fluctuation within this AD are always similar type of fluctuation. So, their multiplication will give us a non-zero value, but outside of these sometime it can be positive, sometime it can be negative. So, on an average there is a high chance that the value will be 0. So, that means when this correlation value is high, means you are within a AD most likely. Okay. So, that is why based on this correlation we can define an integral length scale as well as an integral time scale of a turbulent flow. Okay. Because integral length scale, so on an average if we would like to measure the AD size, it is a random flow, we do not know whether this is the maximum. So, some sort of other ADs also can be present. So, we have to figure it out the signals of all ADs, and based on that we have to take some sort of statistical measure of the size of these ADs, and using this correlation we do so. Okay. So, as we go ahead we will understand little more. So, maybe it is immediately not possible to understand. So, anyway, if it is stationary, then basically this particular value does not depend on the origin. So, that means I can write this as tau is equal to I can write this as 0 and this I can write plus tau. Okay. Sorry, this I can this I can see I can just change the origin T2 minus T1, okay, and this is your 0, okay, and this instead of tau I can write T2 minus T1, right. You see I have changed the origin. instead of taking the u prime data at t1, I have chosen that value to be at t is equal to t1 is equal to 0. That means, to keep this value same, I have to take the value of this value, not at t2, then I have just shift this value, shift this, see, let us say this was our t1 and this was our t2. Okay. So, this I have shifted at this location. To keep this gap same, what I have to do? I have to subtract t1 from this t2, okay, so that my gap remains same. So, that means this particular quantity is actually can be, so this particular quantity now we can write as tau, this gap let us call the t2 minus t1, let us call this as tau equals to, we can write this as t plus u prime t u t plus tau. Okay. It is independent of origin of time, that is what we want. It does not matter whether you take the origin at 0 or origin at t1 or origin at t, it is independent of origin, it is only dependent on this gap, how far the second signal you are considering. Okay. So, that is why r of tau can be written as this. Moreover, this r of tau is symmetric, So, for example, we can write this, we can write this as this can be written as t minus, see, I can again change the origin t is equal to, let me change the origin t is equal to t minus tau. Okay. Let me shift the origin even in the left hand side. If we do that, then this is going to be what, t is equal to t minus tau, and this is going to be t is equal to t minus tau, tau will cancel. So, t prime, okay. And this is equal to what, r of minus tau, okay, sorry, smaller. If this we can write as function of tau, this we can write at same thing, minus of tau, because minus is here. So, r of tau is equal to r of minus tau. So, that means correlation function is symmetric. Okay. So, correlation function is symmetric. Okay. So, this is one important conclusion. Correlation function is symmetric. Okay. All right. Now, see what I can do, I can take this, it is not non-dimensional, it is dimensional, right. So, I can normalize, sorry, this prime is missed here. So, I can normalize such that this quantity becomes non-dimensional. So, very often it is normalized based on this u prime square bar, okay, at origin, okay. And the maximum value of this maximum value, and this function then let us call this function as r of tau, because we have normalized, and the normalized correlation function let us call that capital R of tau. Okay. So, this is what is the normalized correlation function, and based on a data, if we plot this, it is going to come as capital R of tau, which is normalized, the maximum value, it is always 1, it cannot go beyond 1, that this is what is your tau. Okay. So, in a turbulent flow, that correlation function will vary like this if it is function of space, sorry, function of time. If u is a function of space, then instead of tau, here you can put delta x or s. Okay. So, if in that case this can be a function of s. Okay. So, this is what is the correlation function. It may not be clear from this theoretical description immediately that how it is happening, but you need to think physically how it can happen, as well as I will give you some data based on that. I mean, I will give you some data and I will ask you to do this correlation function, calculate this correlation function, which will even make you more familiar with this correlation techniques and why it is coming to be non-zero in a turbulent flow. Anyway, now the question is, if this is the turbulent signal, see there can be many such random signal. Suppose a white noise also, a noise signal can be also any noise signal, this also can be highly fluctuating in nature like this. Okay. So, a noise signal also can be fluctuating in this type of fluctuation can be there even in a noise signal. So, in that case, how to differentiate? It is a this particular signal has come from a noise or it has from a turbulent flow. To check that, if we do this correlation analysis of this signal, for a noise the signal will always be uncorrelated, it cannot have any correlation. But if the signal is coming from a turbulent flow, you do have a correlation like that. Otherwise, if it is noise signal, the correlation will be like this. Okay. There will not be any correlation, only one value, after that all 0. But if it is a turbulent flow, the correlation will be like this. You will always get a non-zero correlation for a turbulent flow. Okay. So, this is what is the correlation. Now, interesting point here, if we consider that small r of tau, this is our correlation function which is not normalized, and capital R of tau we have considered, that is our normalized correlation function, and this one is not normalized correlation function. And if you consider this correlation function, okay, and do the Fourier transform of this function, then we can write s of omega is equal to, by definition, okay, 1 by 2 pi integration minus infinity to infinity exponential I omega tau r of tau d tau. Okay. This is what it is, and this is your the circular frequency omega. Omega is equal to your circular frequency, and it can be shown that r of tau, it can be shown that the r of tau is equal to minus infinity to infinity I omega tau s omega d omega. Okay. So, these two equations are known as Fourier transform pair. Okay. Okay. So, these are known as Fourier transform pair. Okay. Now, some of the interesting thing can be noticed in this particular case. For example, if you consider the first, let us consider this. So, if we consider the omega is equal to 0. If you consider in this case omega is equal to 0, and in this particular case, you know, let us consider that right hand side of this equation, the tau is equal to 0. If you consider the tau is equal to 0 in the next equation, what we get? R of tau is equal to integral minus infinity to infinity s of omega d omega, or what is this? This tau also 0 we have considered. So, this 0 means what is the definition of this? The definition was t u of t plus tau bar. Okay. The tau is 0, tau is 0, that means this is also u of t, this is also u of t, equals to minus infinity infinity dw, sorry, omega, or what is this? You can write this u of t square, right, then bar, right, and what is this? One thing is missed here, this is prime, okay, fluctuation, keep it in mind, we are talking about fluctuation here. So, that means this one you see, this is energy u prime square, fluctuating energy. Okay. So, or this is essentially u RMS square, okay, equals to your minus infinity infinity d omega. So, that means what is SW? SW energy within a band dw, sorry, S of omega is energy within a band d omega centered around frequency omega. So, this is the energy, that means the SW, oh sorry, S omega is your energy spectrum. Okay. So, this is what it says, this is energy spectrum. I think time is over today, we will start again in the next class. Okay. Thank you.